conference service. Please enter your 7-digit
Okay, welcome back. So let's unmute the bridge, Rhonda.
The conference has been unmuted.
Okay, one more chance of using the audio bridge. Any questions? Anything at all? We are all experts on the antenna techniques. No question. We know everything we wanted to know. Continue asking questions through the live meeting medium. Okay. If you like to type in, no problem. Just maximize the use of that medium. Okay. Okay. And by the way, thanks for asking good questions through live meeting. Okay. So now we will turn our attention to the implementation of the techniques that we just looked at. So this is how typical downlink traffic operations should occur. So we have the UEs in a cell, and the UEs will send a report on CQI, PMI, and RI. And to send that, we have the uplink control channel, we have uplink shared channel, and either of the two can be used. Now, our A node B knows about all these pieces of information. So it will execute a proprietary scheduling algorithm, and this is how Alcatel-Lucent can differentiate its products from the competitors' products by designing a good scheduling algorithm. So that algorithm has decided that, okay, let me give certain allocation, some resource blocks, and maybe based on the CQI, PMI, RI, we said, okay, maybe we should do 2x2 MIMO for this user for the downlink. Okay, and maybe we should use 64 com modulation perhaps, and so on. So we make all those decisions and convey those to the user by specifying all those in the control channel. The data itself will go over the big pipe, physical downlink shared channel. Whoever receives the packet through whichever antenna technique will send hybrid reactive positive or negative acknowledgement. Again, that will go over the control channel for uplink shared channel. Okay, we got a question. Oh, yes. Yeah, I remember your PMI question. Your question will be answered very, very soon. Okay, I have a nice example about that PMI. Okay. This is how the physical downlink shared channel would be processed. So let's say I have a transport block, and of course the MAC layer will give the transport block to the physical layer, and we can have up to 2 transport blocks. Okay, so 2 blocks is the maximum. So 1 or 2 transport blocks will be given to the physical layer by MAC. Okay. So let's say we got a transport block, then we add CRC. If it's a big packet, thousands of bits, we will divide into several blocks, code blocks, attach CRC, do the coding, rate matching, so that we can puncture out some bits or code symbols if we do not have adequate bandwidth. Whatever blocks we had come up with, we now combine all the code symbols from all the blocks. Now this is our code work. within a 1 millisecond TTI, that is your transmit time interval, that is your subframe. Within that subframe, we have the capability of sending 1 or 2 code words. So as you can see, whatever comes out of the coding block, that is essentially your code word. Okay. So we can have 1 or 2 code words, and then we scramble the code word is a function of RNTI. This is CRNTI, radio net self, radio network temporary ID. That is the unique ID of the UE as far as the air interface is concerned. Do the modulation. 3 schemes are supported: QPSK, 16 QAM, 64 QAM. Then we have these 2 special processing blocks: layer mapping and pre-coding. Okay, pre-coding will be done using the help of a pre-coding matrix indicator, and we have an outstanding question from yesterday about PMI. So we'll take care of the question when we discuss PMI. In any case, we have modulation symbols potentially modified by this pre-coding mechanism, but those modulation symbols will be sent over specific resource element, meaning specific subcarrier during a modulation symbol time or OFDM symbol time. So one subcarrier and one OFDM symbol, that combination is referred to as resource element. So basically we are placing modulation symbols on specific subcarriers during some OFDM symbol time. Here we have shown you 2 blocks, but there could be a total of 4. If you are sending data from 4 antennas, then you will see 4 such blocks. Okay? Because one antenna will use, let's say, F1, another antenna, same subcarrier F1 for that user when we are doing spatial multiplexing technique. So let's take a look at the antenna specific stuff. Okay, in more detail. We will take a couple of examples of that. Okay, so we will consider layer mapping and pre-coding for spatial multiplexing. And if you want that for transmit diversity, we have some additional information section in the session. So you can look at that, okay, whenever you have a chance. But we'll consider spatial multiplex. Now, what is this layer mapping? Okay. Oh, even before we go there, what is this layer? Okay, layer. Basically, layer is telling us how many distinct modulation symbols I can put on the same subcarrier. So if someone says that I have 4 layers, it means that I can have 4 different modulation symbols, modulation symbol 1, 2, 3, and 4, sent on the same subcarrier, F1, F1, and so on. These are all 4 antennas. So we are able to send out 4 modulation symbols from 4 antennas because we are reusing the same subcarrier F1 4 times. If someone says that, oh, I have 2 layers, I can support 2 layers. In fact, the UE sends a feedback called rank indication, and that rank indication indicates the number of layers, the number of modulation symbols the UE can separate out. Basically, it is the number of antenna signals the terminal can separate out. So if we have super duper excellent channel conditions, maybe the UE can separate out all the 4 antenna signals, then the rank indication will be 4. It means that the base station can now send the information on 4 layers, meaning 4 modulation symbols will be sent from 4 antennas using the same resource F1 subcarrier. So that is your layer. So when we say that we are doing so-called layer mapping, we are just trying to figure out that where should the modulation symbol go. So in this example, I have information coming from this code word, then I do the modulation, and all those modulation symbols I will send on layer 0. I have another code word, I do the modulation, and modulation symbols here are going over layer 1. So it is possible that eventually this will go over antenna 1, this will go over antenna 2, and so on. So layer mapping essentially tells us where the modulation symbols will be going. Will that go over antenna 1, or will the modulation symbol go over antenna 2? So we are just placing the modulation symbols onto specific antenna. Another example, I have two code words and I am able to support 4 layers. So I will use 4 antennas, 1, 2, 3 and 4, but same subcarrier F1. So in this case, my E1 modulation symbols generated from code word 0, that will correspond to layer 0, first antenna. Odd numbered modulation symbols will go over layer 1, that goes to antenna 2, and same thing for antenna number 3 and 4. So in this case, we have 4 layers. So 4 distinct modulation symbols can go over 4 antennas. All those antennas will use the same subcarrier to send those 4 distinct modulation symbols. And we don't need to worry about that because we already told the E node B that go ahead, send me signals from all the 4 antennas. I can easily separate them out. So that will increase our throughput approximately by a factor of 4 compared to single input, single output system. So this is layer mapping. In summary, layer mapping tells us which antenna would eventually be carrying the modulation symbol. Okay. Pre-coding. Okay, so we had one student specifically interested in pre-coding. Now what is this pre-coding? So we are taking an example for spatial multiplexing. This Y is the output of the antenna. So Y0 means antenna number 0 is sending out this specific information. P is maximum number of antennas, physical antennas that we have. So let's say I have 4 antennas at the base station. 1, 2, 3 and 4. So in that case, my P will be 4. So I will have 0, 1, 2 and 3. I will have 3 different pieces of information, 4 different pieces of information going over 4 antennas. So that's what is specified by Y. Now what will go over that antenna? So we just need to do simple matrix multiplication. This W is our pre-coding matrix. Okay. Pre-coding matrix. So we multiply that pre-coding matrix by a vector that includes the modulation symbol. So for example, let's say I have 4 layers because the UE has sent rank indication 4 to the E node B. So E node B wants to use 4 layers. So we will have X0, X1, X2, X3. And this is one modulation symbol. This is another modulation symbol. Right? So we have up to 4 modulation symbols. So I will multiply the pre-coding matrix by a set of modulation symbols. Now let's take a simple example. Okay, someone says that I want to use this pre-coding matrix. So let's say PMI value is, let's say, 1. Okay, and that PMI value goes to the E node B. And that PMI, let's say, corresponds to this specific matrix defined in the standard. So different PMI numbers correspond to different matrices defined in the standard. So let's say, for the sake of this example, the PMI 1 corresponds to this specific pre-coding matrix. Okay. And maybe the UE has said that let's have rank indication 2. I can easily separate out 2 signals. Okay. So now what is actually going over the F? So we have to multiply the pre-coding matrix with the modulation symbol vector. So let's say V is two layers. So I will have modulation symbol 1 and modulation symbol 2. These are 2 modulation symbols. And now I will multiply that by this pre-coding matrix 1 0 0 1. Okay, let me do that. So I am doing matrix multiplication like that. So I will get 1 times x0 plus 0 times x2, and then 0 times x1 plus 1 times x2. So I will get x0 and I am doing 1 and 2. Okay, x1 and x2. I get x1 here and x2 here. Yeah, this live meeting does not do justice to my beautiful handwriting, so it's not that great. But at least, hopefully, you can read my writing here. Okay, y1 and y2. So this will go over antenna 1. This will go over antenna 2. So what is going over antenna 1? Modulation symbol 1. What is going over antenna number 2? Modulation symbol 2. So as you can see, the pre-coding matrix will tell us what we are sending over the antenna, how we are affecting the transmitted modulation symbol. In this example, I did not introduce any phase shift, right? I sent pure modulation symbol x1 from antenna 1 and pure modulation symbol x2 from antenna 2. But it is possible that some other pre-coding matrix will introduce some sort of phase shift. If someone says that, oh, I have only 1 layer, okay, only 1 layer. So in that case, what will happen is I will multiply that matrix. Let's say I have 2 antennas, so this will be 2 by 1. I have 1 layer, okay, meaning my rank indication, let's say just 1. I cannot separate out those 2 antenna signals. They look same to me. So we said, okay, let's have 1 rank, and then I will multiply that by this x. Right? This is my W, another pre-coding matrix. I have 1 layer, so V is only 1, number of layers 1. So I have only 1 modulation symbol, let's say x1. So I will get, if you multiply, you will get x1, x2. So y1, y2 is this. So I am sending out from antenna 1 modulation symbol x1. What am I sending from antenna 2? Same thing, right? I am sending out same modulation symbol. So now those signals will be added at the receive antenna because they are the same, all right? And we have more energy. So think of these like a form of beamforming. So here we are combining the MIMO concept with beamforming. So beamforming here is a special case of MIMO where we cannot separate out the signal. So we said, okay, at least we should have much more focused energy. So UE has told the E node B that this kind of pre-coding matrix gives me the best possible energy, maximum energy, when the rank indication is 1. So E node B has decided to use that. So in summary, pre-coding matrix tells us how we are sending the modulation symbols from the antenna. So sometimes we are sending different modulation symbols from different antennas. Okay. Sometimes if the channel conditions are not so good, then our UE will say that, okay, rank indication 1. So in that case, we will do some sort of beamforming by sending the same information from both the antennas. Here, same information is going from antenna 1 and antenna 2. Okay, so hopefully you got enough information in response to your PMI question. But if you have additional questions, just ask a follow-up question. Okay. Okay. Now we have hybrid ARQ and the antenna technique. How do they interact with each other? Okay, who would tell me the main benefit of hybrid ARQ? Why do we have hybrid ARQ? What is the main goal of hybrid ARQ? Hybrid automatic repeat request. What is the benefit of that? Oh. No benefit? Oh, maybe you are giving me detailed answer. Higher throughput. Okay, very good. Excellent. Okay, and we got one more answer. High bit array, so we need to isolate this from earlier. Okay, very good, very good. So basically, hybrid ARQ, we send a packet, right? And if the UE gets the packet correctly, then it will send positive acknowledgement. So in that case, we do not need to send any additional redundant information. Hybrid ARQ basically minimizes redundancy. We gradually provide redundancy if required. Okay. So in this case, we will not send any redundant information. So instead of wasting our resources on sending the redundant information, why not use those resources to send a new packet? And anytime you use the resources to send a new packet rather than old packet redundancy bits, we are increasing the throughput. Right? So that's the hybrid ARQ. So we minimize redundancy, we increase throughput. And since we are doing the retransmissions here at the physical layer, then upper layer hopefully will not experience a lot of error because we take care of the retransmissions. Most of them hopefully at the physical layer. So we will isolate upper layers from the physical layer. Okay, thanks for your answer. Okay. So whenever you have just single code word transmission, and remember, the code word is nothing but a set of code symbols coming out of the coding block. This code symbol. And as I mentioned, we have support for 2 code words. That's why sometimes it is called multi-code word transmission. Multi-code word MIMO. Single code word MIMO means we just have a single set of code symbols and we distribute the code symbols among all the antennas that we have. But in LTE we support multi-code word, multiple code word, but here 2 code words in LTE. So we support 2 code words. If there is only one code word, then hybrid ARQ will be just for that single packet corresponding with the code word. However, we may have two code words being used. That will be the case when you are using 4 antennas. So whenever you have 4 antenna transmissions, then 2 antennas, let's say we'll use one code word, the other set of 2 antennas will use another code word. Okay. So now we have 2 code words being sent from those antennas. So the hybrid ARQ will be corresponding to those code words. So we will have one ACK or NAC corresponding to one code word, and we will have another ACK or NAC corresponding to another code word here. So we have 2 separate distinct ACKs or NACs whenever we have 2 code words. And the reason for that is we do not want to get stuck with retransmissions. If one code word, let's say code word 1, has been detected okay, so then no need to retransmit that one, right? However, if code word 2 we had some problem, so in that case we will retransmit the code word number 2. So that will make our transmissions more efficient. That is the idea. Okay. We have focused on the downlink because that's where we have multiple antenna techniques primarily implemented. Now what do we have in the uplink? In the uplink we have basically 2 options. So uplink antenna technique. One option is antenna selection. So here we have 2 transmit antennas, transmit antenna 1, transmit antenna 2. However, only one antenna will transmit the signal at a given time instant. So we may have 2 transmit antennas at the UE, but only one antenna will transmit, not 2 at the same time. So that is the antenna selection approach. And the other antenna technique we have is multi-user MIMO. And we already discussed that, right, for the downlink. And the uplink, it would be the same, right? We just briefly mentioned that one UE will be allocated, let's say, subcarrier F1, F2, and then we will have another UE that has been also allocated the same subcarrier F1, F2, and we will separate them through the SDMA beam. So as long as we can separate them in space, we will be okay. So those are the 2 techniques that we support in the uplink. So here we are talking about the antenna selection. So we have 2 antennas, one antenna here, another antenna here. Our E node B is always in charge of resource allocation, and that is the rule. In OFDMA, E node B is always in control. So E node B allocates the uplink resources, and of course we have mentioned that in the past, but the physical downlink control channel that allocates not only the downlink resources but also the uplink resources. And we have one format reserved for the uplink resource, and that format is DCI format 0. Other DCI formats, downlink control information. Other DCI formats are primarily for the downlink resource allocation. But DCI format number 0 is for the uplink resource allocation. So here is our UE getting the uplink resource allocation, and using that set of available resources, it will send the data on the uplink shared channel. So if we have given, let's say, 4 resource blocks, when we send our data using 4 resource blocks, we are using so-called physical uplink shared channel. There is a traffic. What is inside the DCI format 0? So basically, we have the resource block, specific resource block, and for the uplink, it is straightforward. So we give the, let's say, physical resource blocks 3, 4, 5, 6. So we give the starting block number, that would be 3, and then we give the number of consecutive blocks, which would be 1, 2, 3, and 4 consecutive blocks. So those are the 2 pieces of information that we provide as part of the resource allocation. There is only one kind of resource allocation. We can also tell the UE if we want the UE to do frequency hopping or not. So it's possible that we have turned off frequency hopping. It is completely up to the eNodeB scheduler to decide whether to do frequency hopping or not. Modulation encoding scheme. We have QPSK 16QAM, which is the highest order modulation for the uplink. Highest order modulation for the uplink. Who remembers the highest order modulation scheme for the uplink? Oh, one answer is 16QAM. Okay. Another answer 16QAM. Oh. Okay, if I say that there are a total of 3 modulation schemes supported for the uplink shared channel, then which would you indicate? Which one is the missing one? QPS. Oh, okay. So now we got 64QAM. Okay, 64QAM. Okay, so 64QAM is the highest order modulation scheme supported by the standard. Okay. So these are the 3 schemes. Okay. Also, all the 3 are supported in the downlink as well. Now, having said that, here is the situation. We have 5 categories of UEs. So some of you mentioned 16QAM is the highest order modulation. So your answer is the correct one if you are talking about UE categories 1 through 4. And 64QAM is the modulation scheme that is supported only by UE category number 5. So for the folks who said 16QAM, your answer is correct if you are talking about categories 1 through 4. However, we do have this category number 5. That is the only category that will support 64QAM for the up. In the downlink, no problem. All UEs will support 64QAM. All categories, all 5 categories of you. Thanks for attempting to answer the question. Oh, so, and of course, when we say that we have 75 megabits per second maximum peak rate in the uplink, that is for the 64QAM category number 5. So if you just have category, let's say 4, then you cannot get 75 megabits per second. Only category 5 UE will give you 75 megabits per second maximum data rate, but of course that is in 20 megahertz sector. If you only 10 megahertz, you can divide that by 2. Okay, so let's go back to our research allocation. Okay, so we have indicated that also power control command we can send transmit power control command. What do you think? How fast do you think we can send power control commands? How fast? Every how many milliseconds? So E node B, every 1 millisecond. Very good. Okay, excellent. Thanks for the answer. So every millisecond subframe we can send out a power control command. That's why we say that in LTE we have up to 1000 hertz power control. That's how fast it could be. But we are not too much concerned about fast power control in LTE, because within the cell there is no interference ideally because of orthogonal subcarriers. We are worried about the interference coming from other cells. So power control is not as critical in OFDMA as it is for CDMA. So we don't need to worry too much about power control frequency. So 1000 hertz is probably too high for OFDMA. Maybe in OFDMA it could be much less. But it is up to the node B when it wants to send power up-down commands. Of course, we have power control only in the uplink. For the downlink, no power control. Meaning, the UE will not tell the node B, give me more power, give me less power. No power control commands are going in the uplink. So only power control exists in the uplink. So base station sends power up down commands and the UE will increase or decrease power. Okay, and CQI can be requested also. DMRS is the demodulation reference signal. So basically when the UE is sending out the reference signal along with the uplink shared channel, uplink control channel, what kind of beat pattern it should use on the reference signal, that is controlled by this parameter, demodulation reference signal. Okay, so we have constructed this DCI 0 message, and that message is now protected or covered by CRC, cyclic redundancy check. 16-bit CRC, and of course that is masked with the identity of the UE, which is cell radio network temporary ID. Not only that, we mask that with antenna selection mask. So if E node B wants the user to use antenna 0, it will mask it with 0. If E node B wants UE to use antenna number 1 for transmission, then it will mask it with 1. So here E node B can control whether our UE is sending the channel on antenna 0 or antenna 1. But of course, we do not have two antenna signals going at the same time. So when E node B wants to switch from one antenna to another, right, it needs to just do blind switch. It cannot measure the channel conditions on both the antenna signals and then make a choice. So this is blind decision-making process. But of course, we can use the knowledge that it is not highly likely that both antennas will be in a fade at the same time. So when one antenna is in a fade, then our E node B can look at the reference signal quality and make a decision. Oh, that let me try my luck with the other antenna. Maybe the other antenna signal is pretty good. So then it can choose another antenna selection mask, and that will tell the UE that, oh, I'm supposed to use the other antenna. So then it will switch. So in summary, as far as antenna selection is concerned, we can have up to 2 transmit antennas at the UE, But at any given time instance, the UE is sending signals from only one transmit antenna, and the switching of the antenna occurs blindly. And of course, this is an OFDMA system, so E node D is in charge of resource allocation and all these kind of things. Okay, time for me to ask you a question. I will give you, let's say, about 3 minutes. No need to rush. Take your time. Okay, let's say 1 more minute. Thirty seconds. Okay, let's share the results. Okay. 100% correct answer. Very good. So pre-coding and layer mapping will let us know where to put the modulation symbols. And of course, for spatial multiplexing, we would put different information on the same subcarrier. Okay. Okay. So let me summarize the main concepts that we covered today. And once we are done with this, I would give you 2 additional pieces of information. Or maybe I should do that. Okay. So there are 2 things that I would like to briefly go over. Okay. We mentioned that the UE looks at the reference signal to figure out whether it can separate out 2 antenna signals or 4 antenna signals and so on. And we said that they will always be orthogonal. Okay. So the reference signals will always be orthogonal. Okay. So I will show you the structure of that, okay, where we send the reference signal. And another topic that I would like to briefly go over is how E node B conveys the resource allocation to support the antenna technique. Okay, so I will just give you some summary of control channel formats. Now you already have this information in the additional information section. So let me go over that. Okay. So you have this slide in your package. Okay. Okay. We know that E node B conveys the resource allocation, right, by using the downlink control channel. And the way to do that is use specific DCI format, downlink control information. DCI format 0 is for the uplink allocation, but we have other formats that are available for downlink. So for example, if you just want to use one code word, then you can use let's say DCI format 1. If you want to do, let's say, spatial multiplexing, then you can use DCI format 2. And here, since we may be using 2 code words, then we will have modulation encoding scheme specified differently for potentially differently for different code words. So it is possible that from some antennas we are sending out one modulation scheme and maybe different amount of redundancy, and from another antenna we have potentially another modulation scheme being used, and in that case it will make the receiver more complex, but it is supported by the standard. Okay. So we can do different protection for different code words, and that is fully defined by the modulation coding scheme. Okay, so that's the format. Okay. And how do we make sure that the reference signals are orthogonal? Okay. So here is an example. Let's say I have one transmit antenna, and this is time slot 0, half millisecond slot. We are showing you a dozen subcarriers, 12 subcarriers. Okay, the reference signal is sent from first and third last OFDM symbol of a slot. So this is the first one, symbol number 0, and the third last, so 6, 5 and 4, symbol number 4. Okay. So we are sending those in 2 symbols, symbol 0 and symbol number 4. Here. So let's say we are in some cell number 0, and remember there are 504 cell IDs. Out of that, we are in a cell number 0. So in that case, subcarrier F0 carries the reference signal, and then F6 would carry the reference signal. In symbol number 4, F3 carries the reference signal, and this one is F3 plus 6, F9, subcarrier number 9. So within a resource block, 2 subcarriers out of 12 would carry the reference signal. So here in the first symbol it is F0 and then F6, F0, F6, and similarly F9 here and F3, they will be also carrying the reference. So that is if we had only one transmit antenna at the node B. What would happen if we had 2 transmit antennas? So that is the case shown here. So transmit antenna 1, we already know. Okay, so this is the same thing here. That's where the reference signal is. Exactly same thing. So no need to worry about that. It is same thing. So we already know what happens in the case of antenna number 1. Let's see what happens from the second antenna. Transmit antenna number 2. Okay, so we are sending again the reference signal, symbol number 0 and symbol number 4. However, now look at where we are sending the reference signal. It is F3 and this would be F9. Add 6 to that. And similarly, here this is F0 and this would be F6. So as you can see, whenever you are considering, let's say symbol number 0. So during symbol number 0, one antenna is sending reference signal on F0, but another antenna at the same time is sending the reference signal on F3. Same way happens in symbol number 4. Symbol number 4, antenna number 1 is sending out signal here on F3. However, at the same time, the other antenna is sending out signal on F0. So we are using different subcarriers to send our reference signal, and that's what keeps our reference signal orthogonal, and that's how the UE can estimate the channel conditions distinctly for those different antennas, and that's what enables the UE to make a determination whether it should send a rank indication 1 or 2 or 3 or 4, and also what kind of pre-coding matrix, what kind of phase adjustment will give the UE the best possible performance. So I wanted to convey those two pieces of information. Now I will quickly summarize the antenna techniques and under what circumstances we should use them. Okay. So we looked at 3 classes of antenna techniques. Right? So we looked at the diversity technique, we looked at spatial multiplexing technique, and finally we looked at the beamforming technique. Okay, here we have transmit diversity and receive diversity, and the specific transmit diversity that we have is SFPC, space frequency block coding. So we are exploiting space diversity with frequency diversity. So that is the default transmit diversity scheme available in LTE. Okay, we have another transmit diversity, so-called cyclic delay diversity, that makes our static channel dynamic. However, we do not use pure CDD, we use that in conjunction with spatial multiplexing. Not mandatory, but we can have with CDD or without CDD. Both the options are available. Okay, in spatial multiplexing, we have single user MIMO and we have multi-user. And you can think of multi-user MIMO as the combination of spatial multiplexing and beamforming. So what do we do in single user MIMO? Basically, we have multiple antennas, okay, and we are reusing the subcarriers for the same user. So subcarrier F1 carries one modulation symbol, the same subcarrier from another antenna carries another modulation symbol. Okay. And the reuse of the subcarriers will increase the throughput. So the main benefit of this is higher throughput. Here we have exploited space and frequency diversity. So this will improve the reliability. Multi-user MIMO. So here we are sharing the subcarriers among different users. And basically within a 120 degree sectorized region, I have created two beams, and since I am reusing the subcarriers, let's say F1 here and F1 here, I'm again able to increase the capacity, increase throughput. That is right. So these are the beams that we have created. And beam forming, basically rather than spreading energy, right, all over the place, which we do in traditional sectorization, rather than that, we said, okay, let's just focus energy in a given direction. But in LTE, we do not have pure beam forming. We use beam forming along with the MIMO technique. So we have pre-coding that we do along with the spatial multiplexing. So we have some level of beam forming, not full-fledged adaptive beam forming, but some level of beam forming is supported in LTE. Okay, so all these are supported for the downlink, and the benefit of beam forming type technique, it will increase throughput and it will significantly increase cell edge performance. So you will get pretty good data rates at cell edge. If you allow brand new sort of link budget, okay, you are not constraining your cell size, then you can even increase your cell size because of the beamforming signal can propagate much farther from the base station. And as far as the uplink is concerned, we have multi-user MIMO support HTML, and we support the antenna selection, transmit antenna selection. Okay. So now finally, channel conditions and the antenna technique. If we have good channel conditions, good CQI, high value of CQI, then you can use MIMO technique, spatial multiplexing. If you have poor channel conditions, right, then you can use transmit diversity. Okay. For example, SFDC. Okay, and you can do beam forming. Here you can do rank indication 1, meaning you are not sending different modulation symbols from different antennas. You can just send same information from different antennas. So F1, you are sending modulation symbol S1. F1, you are sending modulation symbol S1, and they will combine at the receiver. So now you have more signal energy. So poor channel conditions, you can exploit transmit diversity or beam. Okay, so that's what I wanted to convey. Any questions? So let's unmute the bridge, please.
The conference has been unmuted.
Okay, any questions related to the antenna technique? I'm going to make sure that all the things that oh yes. Oh, just the background noise. Okay.
Yeah, I have a question.
Oh, okay. Yes, please go ahead.
Uh, just now you said if a channel is in good condition, then is it the UE would do CQI algorithm?
Oh,
is
okay.
it UE or B?
Oh, okay. So this is what happens. Our UE is periodically sending out CQI, let's say on the uplink control channel. And when the CQI stays good for several subframes, let's say CQI 12, after some time 13, then 14, then 12, 14, etc. So eNode we will observe such CQI reports, and now eNode we will be comfortable that yes, the UE has reported excellent channel conditions for a reasonably good time frame. So now let me switch to Mnemotech.
Okay.
Okay.
So
yeah. Good
this
question.
is in the
Good
eNode B. All right. Thank you.
Okay. Any additional questions? Anything else? Any other question? I give away the control to Rhonda. Any other question? Okay. So Rhonda, let's send the evaluation to the student. But thank you guys. Thank you very much for asking very good questions. And we hope to talk to you again in a future session. As in the past, I will send you soft copy of the class notes, and feel free to send me email if you have any additional questions. So again, thank you. Rhonda, you are in charge now.
Okay, thank you, Nisha, and thank you, everybody, for attending. I know it's been a long afternoon, but this is some very worthwhile information, and we certainly appreciate you hanging around for just a couple more minutes to give us your feedback. Nisha and his team takes the feedback seriously, as well as those of us here in the university, so we certainly value your input. You can go to your full screen using your F5, and you can answer the survey right here on the screen, the same as you participated with the polls for Nisha. So please provide us with that information. It should only take a couple minutes. And then for those of you who might have some questions or need some more diagrams drawn by Nisha, as soon as we finish with the survey, he can go back to the information and draw for you. Otherwise, just feel free. The bridge will remain open. Feel free to ask your questions now. We certainly appreciate it, so thanks again.
Oh, I see. So that A, okay, so remember I took example A and B, right?
So I'm assuming that one part will be real part and one will be imaginary.
Oh, okay. So that.
So so we can use the metrics and for multiplying stuff and retrieve it back on the either side. So I would like to see how this will be modulated on top of how the signal will be modulated on top of the frequency.
I see. Okay, I will give you a simple answer. Now, unfortunately, I cannot draw, okay, because you are still filling out, you guys are filling out the survey.
Yeah, we can wait until they finish the...
Oh, okay. But in the meantime, I will give you some information.
Okay.
So basically, what we are doing is, think of that A as your modulation symbol. So it is a complex number, okay, and then B is another complex number. Now, that A complex number goes over one subcarrier, so it goes into the IFFT. Okay, so at the transmitter, let's say modulation symbol A will go over subcarrier F1 from one antenna. So we are doing IFFT, sending that signal from one antenna. Then modulation symbol B will go over the same subcarrier F1, but from another antenna, because another antenna is also sending out the IFFT signal. So we have one IFFT creating signal for antenna 1, another IFFT block creating the signal for antenna number 2. Now those are now sent over there. The receiver will do the opposite processing. So now we have two FFTs. So one FFT will process the received signal, okay, and on a given subcarrier, it will find the combined signal, okay, which has two modulation symbols, right, A plus B. So in practice, it would be A would be a complex number with real and imaginary parts. B also a complex number, imaginary and real part. Okay. So now we have some combined signal A plus B, two modulation symbols on F1 at receive antenna 1. Similarly, another combined modulation symbol, let's say A minus B, on receive antenna 2. In the based on the observation of reference signals, we have come up with the spatial signature. So we saw that it was 1, 1 and 1 minus 1. So the receiver will then apply those spatial signatures that it has predicted by observing the reference signals. It will apply those to the modulation symbols on F1 that it got from receive antenna 1. It will apply those signatures to F1 subcarrier that it received at antenna number 2, and then it will be able to retrieve the signal. So in practice, the modulation symbol still will go over specific subcarrier, and it will pass through the regular IFFT block at the transmitter and FFT block at the receiver. But I will draw that picture.
Also, like how when like modulating a complex number to a wave, how this is going to be like.
Oh, I see. I see. Okay,
like it's going to be shifted, or I couldn't imagine. I would like to see how it is in terms of modulation.
I see. Okay, yeah, so let's wait.
Okay.
2-3 minutes. Okay, sure. Okay, stay here. Okay, please wait. We'll give 2 more minutes. Okay, I'll be back in about a minute. So do not go away anywhere. Please stay around. Okay, so what I was saying is here is our transmitter. Okay, and modulation symbol F1 that will be on F1, symbol 2 on F2, etc. And then we do IFFT, and IFFT will generate some samples. So let's pick this sample. So it would be, let's say, alpha times S1 plus beta times S2 plus gamma times S3 and so on. So these are sort of complex numbers. Okay, and S1 is of course on F1 subcarrier. S2 is on F2. So you can think of, okay, let's focus on this F1. Okay. And let's have QPSK modulation, that would be, let's say, something like 1, 2, 3, and 4. Okay, S1. So this is the I channel, this is the Q channel. So this is the cosine wave, and this is a sinusoidal signal. Okay. Let's say the amplitude is A. So A sine wave, that would be one symbol S1. Let's say the symbol S2 is here. So then it would be negative A and the sine wave. Now, we can still talk about the baseband, so it will be 2 pi f1. If this goes over f2, it will be 2 pi f2. Okay, let's do that. So now f1, this is A amplitude here, A sine wave. However, S2 is negative sine wave, so it would be something like that, minus A sine wave, S2. So the IFFT is now multiplying by some number, let's say alpha times this A sine wave plus beta times S2, which is minus A sine. We are adding these amplitudes after doing some sort of scaling. So maybe this corresponds to this time instant, then this corresponds to another time instant here, and finally perhaps let's pick this time instant. So you add them after scaling, and that will be maybe this time instant. Okay. And after you do that, then you can do frequency up conversion, and that will bring the signal to the RF, and maybe 700 megahertz in the US. Okay. So that's what will happen. But we can still talk about the baseband. So as you can see, the IFFT itself generates this kind of signal, all these samples. Now I'm drawing sort of continuous wave, but in practice it's a discrete signal. These are all samples, discrete signal samples. Okay. And they represent scale multiplications of those sinusoidal signals, sine and cosine waves. Okay. So as far as the antenna techniques are concerned now, okay, so we have one antenna here, antenna 1. So it is getting signal from this IFFT, okay, FFT1. So here let's say we had the S1 on F1. Then same thing will happen with another IFFT, antenna 2. So let's say we have some other SX on F1, same subcarrier. At the receiver, we have two, let's say, receive antennas. Receive antenna 1 and 2. So first they will do the let's say, after frequency down conversion and so on, we will do FFT here, FFT2. So this will give you your subcarriers back, F1, and on that we have modulation symbol, S1 plus, okay, like actually, let's say gamma times S1 plus, let's say, theta times Fx. When you do FFT here, on F1, you will find, let's say, delta times S1 plus, let's say, rho times Fx. And we have these coefficients. That's how the environment has changed our transmitted signal, impact of the environment. Okay. So let's say we have in the past observed reference signals, and they are all orthogonal signals, right? So we will be having this knowledge of gamma and theta and delta and rho. This is nothing but your spatial signature component. Okay, this is how we'll be able to recover the signals. So in the simple example that I showed you earlier here, right, this is 1, meaning maybe most of the parameters, what did I use, some theta, right, delta, gamma, all those are 1s, nothing, only row is -1. Okay, so we are able to sort of recover the signal by using those components. Maybe we need to do inverse operations, but you got the basic idea, right? That we are able to predict those based on different signals and then recover the original signal. Does that make sense?
Okay, yes, thank you very much. This is very good.
Okay, you are most welcome. Okay, any other question? Anything at all? I will start my 1-minute timer. No question for 1 minute, then we will formally end today's session. And again, thanks for asking good questions. "30 seconds to go." "10 seconds." Okay. Okay, again, thank you very much, folks. Thanks for staying a little longer. And I will send you the class notes. Rhonda, now you are in control again. Or did we lose you?
No, I'm still here, just having a little bridge. Okay, so thank you, Nisha, and thanks everybody for sticking around. Thank you for filling out that survey, and thank you for participating in today's class. And so I think there's another class. What is tomorrow? Thursday, Friday. Yeah, we have Thursday, Friday sessions. So Nisha, you take care until we talk again.
And you want to store the other file, right? With the annotation.
Yes, I'm going to grab that right now before you disconnect.
Yeah.
So if you need to drop the bridge, you can go ahead, and then I'll grab that file.